So when you see that word inverse, I want you to think opposites. And these are mathematical opposites. So how we find this mathematical opposite is we switch x and y. We're inverting our input with our output. Now there are two aspects of inverses that we will be looking at. The first is how do we find them algebraically? And the second is how do we find them graphically? But no matter which method we're using, we're still doing the same basic thing of switching x and y. So if I wanted to algebraically invert an equation, we would first replace f of x with y. Then we switch x and y, so there's the part that makes it an inverse. And then we resolve for y. So I want you to write resolve in there. We resolve for y. And then you write the inverse equation. This is our notation for inverses. And just like with our linear programming problems, you had to memorize that f of x, y notation. This notation is read as the inverse of f of x. So how it's written is f to the negative 1 of x, but what it actually is read as is the inverse of f of x. So we're going to see what this looks like in the example below. I have this equation. It is a linear equation. If I want to find the inverse of this equation, the first thing I would do is replace that f of x with y, because those two mean the same thing. So replace it with the output variable. Then we switch x and y, and we only switch x and y. Notice that that coefficient of 2 stays locked in on the right side. So literally the only thing you are switching is the variables themselves. Where you have a y, put an x. Where you have an x, put a y. And then we resolve the equation for y. So how am I going to get y all by itself? We're going to divide both sides by 2. So divide by 2, divide by 2. And that gives me y equals x over 2. And my final step is replacing the y with that inverse function notation that says, hey, this isn't just any old line. This is the inverse or the mathematical opposite of this line that we started with. So notice that they have 1/2 x. Having x over 2 is the same as having 1/2 x if you throw a 1 in front of that. The only reason why we kind of prefer this form or the final form of this is it looks more like slope-intercept form versus having x over 2. Like, wait, what's the slope? So it's a good idea to kind of separate the coefficient from x. So that is how we find our inverse algebraically. Now for finding the inverse graphically, we first graph our original function using slope-intercept form, x and y intercepts, or using transformations. So there they are. This is why I wanted a solid on transformations before moving on to this. So you graph the original function, creating a table of values for that function, and then you create a table of values for the inverse by, there it is, switching the x's and the y's. So I switch the x and the y in the equation to find the inverse. And if I want to invert a table of values, we invert each of the individual coordinates. So I'm going to switch my x and y to go from this original table of the function to this inverted table. And again, that label is important because this shows me this isn't just any old linear equation. It is the inverse of f of x. So folks, all of these points are points on that linear function. If I plug in 0, I get 0. If I plug in 1 for x, 2 times 1 is 2. If I plug in 2 for x, 2 times 2 is 4 for the output. Plug in -1, 2 times -1 is -2. So there's our input-output table for this line. Let's say I don't know how to graph the inverse. I'm looking at inverse of f of x is 1/2 x. I'm like, I don't know how to graph that. What we can do is switch each of the x and y's in each of those coordinates to get our inverse coordinates. So what happens if I flip-flop 0 and 0? We get 0, 0. What happens if I switch 1 and 2 around? We get 2, 1. If I switch 2 and 4 around, we get 4, 2. -1 and -2, we get -2 and -1. So the whole crux of this is we are always switching x and y. However, sometimes solving for the inverse equation gets kind of messy, and sometimes doing the graphs can get a little bit messy for our other functions. So let's go ahead and turn the page. Actually, no, before we turn the page, there's one other thing we're going to add about inverses down at the bottom. Inverses reflect across the line y equals x. This is a property of inverses, and it's going to be kind of a check for us as we start doing these inverse problems. And now we're going to turn the page. So on these problems up at the top, we are given two graphs. And what we want to do is find the inverses. So I've got a quadratic. And I am going to label this f of x for the original function. In order for me to invert a graph, we are going to pick 3 points. Pick 3 f of x points and invert them to make f to the -1 of x, or the inverse of f of x's table. On this page, please, 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 please make sure that you include your labels. So I have labeled this equation f of x. We're also going to label our table f of x. Now, I'm going to pick 3 points, kind of similar to what we would do with our parent table or like a transform table. So I'm going to center it around my vertex, 0, 0. And then I'm going to pick my next point on the grid to the left, and then my next point on the grid to the right. This one up here is at -2, 8. So -2, 8. And then this one over is at +2, 8. This is our function, f of x. And this is f of x's table of values. So to find the inverse, first the notation, it's written as f to the -1 of x, but it's read as the inverse of f of x. And we're going to switch all those x's and y's. So what's going to happen to this point, -2, 8? 8, -2. We just flip-flop the coordinates. 0, 0 is going to stay 0, 0. If I flip 2, 8, it becomes 8, 2. And now I plot these points. So 8, -2, boink, 0, 0, boink, and 8, 2, boink. And it's like, ooh, how are we going to draw this and connect these dots? This is where we're going to go back to that definition that we wrote on the previous page that says inverses go over that line of reflection, y equals x. So line of reflection, y equals x. We're actually going to draw that line of reflection as a dashed line. This line goes through 0, 0, because that's its y-intercept, and it has a slope of 1 over 1. So here's 0, 0, here's up 1 over 1, up 1 over 1. It's pretty much going to go up through those squares. And then pew, 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 pew. Now, we have been reflecting with transformations going top over bottom, flipping it over the x-axis. Here, instead of flipping over one of the axes, we are going to be flipping it across that line. So I'm going to show you what reflecting this looks like. We are going to take this point and move it an equal distance across that line. So I swivel it over the line to the other side. This point, I swivel over the line to the other side. Why doesn't that point move? Because it's on the line. Similar to how when we do a vertical reflection, when I have something like this, here's an absolute value graph. When I reflect that, and that's the only transformation that's happening, the point or the vertex that's on the x-axis does not move. So anything that's on the line will not move. So each of those points moves an equal distance across that line, and what I end up with is this kind of sideways parabola. Swoosh. Try to make it look more like a U and not so pointy. And we're going to label this one the inverse of f of x. So inverse means we switch x and y around, and what happens to our equations or our graphs is they flip over this line y equals x. Why do you think it's this line, y equals x, and not some other line? What's special about this line? All of the x and y values are the same. So 0, 0 will stay 0, 0. 1, 1 will stay 1, 1. And when you flip the x and the y coordinates, they swivel to the other side of this line. What questions do you have so far? When I say inverse, you think opposite. And opposite of what? Switching your x and y around. Output becomes the input, and input becomes the output. Let's go ahead and try this next one. We've got this line. Woo! Label it f of x. Yeah. So there's our original function. We're going to pick 3 points on this line. So let's do that to the right of this graph. We're going to label the table f of x. And let's just move from left to right. 0, 3 is a good point. Make sure it's 0, 3 and not 3, 0. 1, 1 is a good point. What's a good third point? 2, negative 1. And careful, folks, this is kind of a funky graph scale that each box is a small decimal amount and the big boxes are each 1 unit. So there's our original function. Our inverse function is we're going to switch each of those coordinates. So 0, 3 becomes 3, 0. 1, 1 becomes 1, 1. And then 2, negative 1 becomes negative 1, 2. Plot those points. 3, 0, boop. 1, 1, ooh, same point. And then negative 1, 2. And we know how to draw lines. It's just going to be another straight line. and make sure you label that the inverse of f of x. And we are now going to put up the line of reflection and see if it looks good. We go through 0, 0, and up 1, over 1, up 1, over 1. Down 1, back 1, down 1, back 1. So does it look like our original function point reflected across the line? Whoops, missed the point there. Over to the other side. Yep. This point stayed right where it is because it's on the line. And then this blue point reflected in the other direction over the line. So it always moves to the opposite side of the line in equal distance. And we have labeled that the inverse of f of x. Folks, that's it for today. In your homework packet, you can do 23 through 26, and you must show both tables as part of your work. If you didn't turn in page 4 yesterday, that is what is due tonight. So turn in page 4 if you haven't already, and you can start working on those 4 problems.
But it's not due tonight.
Not due tonight, correct.